Traveling to Mars and building a settlement there is the new goal of this space race. But let's be quite honest, sending humans to Mars isn't an easy task. The furthest humans have traveled into space is to the dark side of the Moon, which is just 400,000 kilometers away. Traveling to Mars is much more complex than that. It is a journey that could take months, if not years, and would require humanity to overcome many technological challenges. But how long would it take us to travel to Mars based on our current technologies? And can we decrease that time with technological advancements? The answer is a big yes. How? A journey to the red planet is not measured in days or weeks, but in months and sometimes years. It demands technologies that push propulsion, navigation, life support, and human endurance to their absolute limits. So, the real question is not whether we want to go to Mars. The real question is how long it would actually take us to get there using the technology we have today. And just as importantly, whether future advancements could dramatically shorten that journey. Mars has remained largely unexplored for a reason. Only a handful of robotic missions have successfully landed on its surface, and every one of them faced extreme risk. Deep space is filled with challenges that make a crewed voyage to Mars far more complex than any mission before it. Radiation exposure, limited supplies, psychological strain, and the vast emptiness between planets all stand in the way. For generations, a human mission to Mars belonged to science fiction. But today, that vision is rapidly turning into a real engineering problem. Two major forces are shaping this future: NASA and SpaceX. Both are committed to sending humans to Mars, yet their philosophies could not be more different. NASA prioritizes caution, redundancy, and long-term reliability. SpaceX embraces rapid innovation, bold testing, and calculated risk. Despite these differences, both organizations understand one crucial fact: reaching Mars will require cooperation. By combining experience, funding, and technological breakthroughs, the path to Mars becomes far more achievable. To understand how long the journey might take, we first need to understand distance. Mars is the fourth planet from the Sun and, after Venus, Earth's closest planetary neighbor. But the distance between Earth and Mars is constantly changing. Both planets orbit the Sun at different speeds, following elliptical paths that shift their positions over time. In theory, Earth and Mars can come remarkably close. The shortest possible distance occurs when Mars is near its closest point to the Sun, and Earth is near its farthest. In this rare alignment, the planets would be separated by just over 50 million kilometers. While such a perfect alignment has never been recorded, Earth and Mars came close in 2003, reaching a distance of about 56 million kilometers. Realistically, most missions must account for much greater distances than this ideal scenario. Now, imagine traveling to Mars at the fastest speed allowed by physics, the speed of light. At its closest approach, light would take just over 3 minutes to travel from Earth to Mars. At its farthest, it would take more than 20 minutes. On average, light would cross the distance in around 12 minutes. These numbers highlight how vast space truly is, but they also reveal a critical limitation. Traveling at the speed of light is not something our current technology can achieve. So what about the fastest spacecraft humanity has ever built? One of the fastest missions ever launched was NASA's New Horizons spacecraft. Designed to explore the outer solar system, it reached extraordinary speeds shortly after launch. If a spacecraft traveling at similar speeds were sent directly toward Mars, the journey could take just a few months under ideal conditions. When Mars is farther away, that trip could stretch closer to a year. At its closest, the journey could theoretically be completed in just over a month. Then came an even faster spacecraft. NASA's Parker Solar Probe shattered speed records as it plunged toward the Sun, using gravity to accelerate to velocities no human-made object had ever reached. At peak speed, it became the fastest spacecraft in history. If such speeds could be sustained on a Mars-bound trajectory, travel times would shrink dramatically, on paper. But this is where reality intervenes. All of these estimates rely on a flawed assumption that a spacecraft can travel in a straight line through space. In reality, planets orbit the Sun, and spacecraft must do the same. You cannot simply point a rocket at Mars and fly directly there without crossing the sun's path. Instead, spacecraft follow carefully calculated arcs that conserve fuel and align with orbital mechanics. Another complication arises even during close planetary alignments. These calculations assume Mars remains stationary while the spacecraft travels toward it. In truth, Mars continues moving along its orbit the entire time. Engineers must predict where Mars will be months in advance, not where it is on the day of launch. This makes mission planning incredibly complex. According to NASA, the most efficient missions to Mars take advantage of precise planetary alignments that occur roughly every 26 months. During these launch windows, spacecraft can follow what is known as a Hohmann transfer orbit. This curved trajectory allows a spacecraft to reach Mars using the least amount of fuel possible. Using this method, the journey typically takes about 9 months. Any attempt to go faster would require significantly more fuel, reducing payload capacity and increasing costs. A round trip using current technology could take nearly 2 years, not including time spent on the Martian surface. There are other factors as well. Spacecraft must slow down upon arrival to avoid overshooting Mars entirely. Life support systems must function flawlessly for months. And astronauts must endure long periods of isolation, confined spaces, and exposure to cosmic radiation. Because of these constraints, missions to Mars can only launch during narrow windows. Miss one and the next opportunity may be more than 2 years away. This rhythm dictates everything from spacecraft design to mission timelines. So where does this leave humanity today? Right now, the most ambitious effort to overcome these challenges is coming from SpaceX. Elon Musk's vision centers on Starship, a fully reusable spacecraft designed specifically for deep space travel. At the heart of this system are the Raptor engines, which generate enormous thrust while maximizing efficiency. SpaceX is continuously refining these engines, pushing toward improved versions that are more powerful and more reliable. But what truly sets Starship apart is reusability. By dramatically reducing launch costs, SpaceX aims to make frequent Mars missions economically viable. This approach could allow for larger payloads, faster iteration, and ultimately, sustainable human presence on another planet. Starship is designed not just to reach Mars, but to land there, refuel, and return. It represents a shift from single-mission exploration to long-term planetary infrastructure. While enormous challenges remain, the foundation is being laid. Humanity may not be ready to travel to Mars in weeks or days, but we are steadily closing the gap. Each advancement in propulsion, navigation, and spacecraft design brings the Red Planet closer. If you enjoy deep space storytelling and want to follow humanity's journey beyond Earth, make sure to subscribe to Astreon for more cinematic space documentaries. So now the question is yours. Will humans build a settlement on Mars within our lifetime? Or is the Red Planet still farther away than we think?